All right, Algebra 1, this is 2.04, examples 1 and 2. Suppose the upfront construction cost for green features in a school would be $300,000. In return, the annual savings from the green features would be $75,000. There's a linear relationship between time and the total savings that add up from the green features. Analyze this function by answering the questions below. What is the independent variable? So the two variables that we have identified here are time and total savings. Those are the two things that we're interested in. And it turns out here that time is the independent variable. When time is involved, it's almost always independent. The other variable will be determined by the independent variable. So how much savings there is depends on how much time there is. That means total savings is the dependent variable. Total savings is the dependent variable, and time is the independent variable. So I'm just going to mark those accordingly. What is the slope of this linear function? Well, slope is something that changes. And so the thing that's changing here is it is an annual savings. So yearly there is a savings. So the savings increases by $75,000 per year. So the slope is 75,000 per year. The y-intercept is in year 0. So before we start saving any money, the y-intercept will be negative $300,000. Now, why is it a negative $300,000? Well, the dependent variable, the y variable, is total savings. There are negative savings because there are costs. So it's a negative $300,000 savings, and that's so it's a coordinate point. Oops, I did that all wrong. It is point 0, negative 300,000, not negative 300,000, 0. All right, now let's put the equation together in slope-intercept form. So here we have our slope, which is 75,000. That's going to be our m value. And we have our y-intercept, negative 300,000. That's our b value. So our equation will be y equals negative 300. Whoa, going all over the place. Will be 75,000 x minus 300,000. And so we have our negative 300,000 right there. We have our 75,000 right there. Make a graph of the equation. Well, that means that our y-intercept, so the place where the line crosses the y-axis, is negative 300,000. So that's going to be right there. I'm going to make that red just so that we know where it's coming from. And then each year, so these are the number of years. Each year, so each time we move to the right once, we go up 75,000. So up 75,000 from negative 300,000 will be negative 225,000. We move to the right another year and go up another 75,000. And so this is going to be our pattern right there. And we can connect those then with a straight line like that. So we can see that our delta y is 75,000. Our delta x is 1. Our y-intercept is negative 300,000. What is the x-intercept? And what does the x-intercept represent in this situation? So it looks like it's 4 right here. And I'm pretty sure it is, but we need to check. So what we do is we put 0 in for y, because when that line crosses the y-axis, the y value is, the x-axis, the y value is 0. So what we do is we say, all right, we have 0 is equal to 75,000 x minus 300,000. And then we're going to solve for our x value there to figure out when it actually happens. So we're going to add 300,000 here to both sides. And we'll get 300,000 is equal to 75,000 x. And in order to solve there, we need to divide both sides by 75,000. And when we do that, we get 4 is equal to x. And what that means is, so the savings is 0. It's not negative. There's no more owed. It's not positive. We haven't started saving positively. So that's at the break-even point. So what we can say here is that in year 4, I'm probably going to be in the way here, year 4, we break even. We haven't saved any, we haven't spent any extra, it's just the break-even point. And that is our first example here. Here's the second example. After being launched into orbit, a communications satellite stays in place above the same spot on Earth by moving through space at the same speed as the rotating Earth. The satellite uses a small amount of power each day to maintain its constant height above Earth. When the power supply on board is used up, the satellite is no longer functional. The satellite has 100 units of power when it is launched into space and 0 units of power during year 10. This means that for every year, the function loses 10 units of power. Determine the equation for the linear function that represents this scenario. So in this case, again, we have time, that is our independent variable, time in years. And the dependent variable then is the units of power it still has remaining, units of power remaining. So the slope of this, it says that it loses 10 units of power per year. So that means that our slope is -10 or -10 over 1. And the y-intercept then is where the units of power that we start with. We start with 100 units of power. So it is the point 0, 100. And now if we're going to write an equation for this, so we have f of x is equal to our slope, -10, x, and we have a positive 100 y-intercept. And that is the equation, the slope-intercept form of the equation in function notation. So that is our second example.